about Autosar. Autosar is the automotive software specifically used for the configuring of the framework. So to understand in detail about the Autosar, here the agenda is the introduction of the Autosar specification, application scope of Autosar, and the architecture overview of the software layers. It includes architecture overview of the software layer, includes the microcontroller abstraction layer, ECU abstraction layer, complex drivers layer, and services layer, Autosar runtime environment, and next we'll focus on how these Autosar components and tools can be configured and the benefits of Autosar. And coming to the introduction of Autosar, Autosar stands for the Automotive Open System Architecture. So the main goal is to develop the software for the manufacturers and suppliers. So Autosar provides the framework for development of the automotive software and enabling the interoperability among the components from different manufacturers. It defines as a layered architecture and standardized interface. And allowing the vehicle manufacturers and supplier to focus on specific parts of the system without worrying about compatibility issues. In vehicle, why this software is used? It is used to monitor the real-time constraints and the critical things, critical functionalities or critical applications which can be handled easily for the automotive software components. So, for example, let's consider there are OEMs which work for the software. The BMW, Daimler, Toyota, General Motors are the OEMs. They even require the software which essentially to monitor the real-time constraints. So for the hardware, we have the software configuration. So that software and hardware will be supplied by specific ECU owners who is responsible for the hardware and software integration. And they give the software and hardware specific to the ECUs. Example, if you think that it is the engine ECU, and this we talks about the powertrain ECU, and we talks about the infotainment ECU. So for related to the engine, the engine software is developed. For the powertrain ECU, we require the software, powertrain software. Similarly, for infotainment, we have the infotainment software. So that will be developed by the ECU owners who, and these OEMs, they need to configure these hardware in the vehicles. So that will be integrated, and they need to ensure that these ECUs are interlinked with each other and they are establish the communication. So it is a part of the scalability and the portability, how that can be configured for the respective vehicle. And for the developing the code, the software for each and every hardware, the code will be developed and it will be tested in the virtual platform and the real vehicle, how the sensors are really performed in the real time. So the components wise, they should develop for each and every ECU that present in the corner of the vehicles. It aims to provide the scalable, modular, and standardized the approach of the automotive software to develop and develop the software. The main intention is to reduce the cost, and the complexity is adding more and more in the vehicles. That should be reduced. How this can can be configured? The key features of the Autosar includes the modularity. So modularity talks about it talks about how the software is divided and divided into the module component. Software is divided into the modular component, and that can be reused. and that can be reused to across the different vehicle platform. Next, we have a scalability. Scalability talks about how it can support the wide range of automotive applications from basic functionality to more complex systems in the autonomous driving. And next, we have a interoperability. So interoperability, it talks about how different components from different manufacturers can work together simultaneously. And next we have a separation of concerns. So here the hardware and software is separated, and that will be separated, meaning here is the software can be developed independently of the hardware platform. They will mainly focus on the software functionality, how the interfaces can be configured. They initially they won't worry about how the hardware things, they mainly focus about the software implementation. If you see the here the example, so here, the components of the vehicle, it's essentially the engine and the powertrain, airbags, and the ECU network and infotainment are the different components which have. For all together, the software is developed. And once the software is developed, now the vehicles, they need to release variant 1, variant 2, variant 3 in the market. So to release the market, the same software with respect to the variants, they change the variant naming and they will release into the market. So this complexity of the softwares will be added depends upon the variants in the vehicles. So the history about the establishment of automotive. So Autosar was established in 2023 by the automotive manufacturers, and the primary goal was to address the growing complexity of the automotive electronics, which results from increasing the demand of features such as the ADAS or powertrain, battery relevant, and the infotainment systems. And the software here, the initially it was available in the conventional, where the application software and the hardware will be they configured. So the based upon the hardware, the hardware software application will be configured, and whenever they need to change the application, the hardware also keep on changing. It is a part of a conventional hardware issues. Later, the focus is this: they develop the standardized software. They keep on work for the upgrading of the code, and they will keep working on the future hardware upgrading parallelly. It is a parallel process where the upgrading can be happened, and even if they need to remove the functional feature, that can be easily removed. It is a part of a scalability or the portable, how that can be changed or modified anything between the hardware and software. So the Autosar architecture is came into the picture. It is a framework that established between the hardware and software. The framework help the configuring is very easier in the real-time environment. The main difference between the hardware and software is here the application software and the hardware is independent, and here it is independent towards the Autosar architecture framework. And it is a larger effort for relocating the functionality. It is a simple process where the reusing of the software is very easier, and it is the software can be developed very easily for specific functions in it. So Autosar is categorized into two platforms. The first part is the Autosar Classic platform. It is the original Autosar platform, specifically designed for the real-time and safety criticality systems. So mainly they focus, and we have the other platform is the Autosar Adaptive platform. It is a newer platform specifically designed for more complex and high performance computing environments, such as the ADAS, Advanced Driver Assist System, and the autonomous driving vehicles. and it supports the dynamic software updates, and it have the specifically this adaptive Autosar platform will be configured for the based on the service oriented architecture. So we go in detail to understand about those difference. The difference here is the Autosar classic and the adaptive Autosar, it have the difference. Based upon the target system, we choose where the real time or the safety critical or resource constraints issue that required for the classic Autosar that can be chosen. And if it is a high performance, we choose the adaptive Autosar. And the configuration is, it is a part of a static configuration. Classic and auto adaptive is the dynamic that can be run at configure at runtime. This is at the phase of design only we need to configure. And we the Autosars, we have the OS, specifically the OEX SEK is and not OPEX, and here we have OPEX components. So it have a different platforms of OS that we use for the classic and adaptive cluster. And we have a architecture. It focused on the layer and it have the service oriented architecture OS. And the protocols is essentially for classic Autosar and adaptive classic. If we compare the protocols, the primary, the CAN, LIN, FlexRay are the classic Autosars, and adaptive Autosars, we have the Ethernet, some IP, and TCP IP. And we have the application domains, the ECUs, powertrains, and the body control chassis orders. We use the classic Autosars, and adaptive classic Autosar, we have the autonomous driving and VTX infotainment and some of the other ECUs that functionalities can be added. And safety standards, mainly both Autosars, it should follow the ISO 2626 compliance, but and moreover the complexity is added more. The safety critical things will be focused more on the flexibility and scalability. So here the scalable is a how the simple the issue and how we are able to configure easily. And here the high scalable for complex system and the services. Performance wise, the real time, and it is a real time and resource efficient. It is a high performance computing and multi-core support. And dynamic updates, it's no support for dynamic updates. It supports the mostly the order. So uh, over the year, the softwares can be updated very easily and efficiently for the adaptive Autosar. So these are the two major Autosar platforms. It should be understand. And for Autosar, the common is the architecture layer. We need to understand in detail. And before understanding that, what are the key objects of Autosar? We have a standardized. It provides the common standards for automotive software, and it enables the interoperability across the different manufacturers and suppliers. And scalability, it should be supports both simple and complex issues, make it suitable for a wide range of application. And reusability, it facilitates the reuse of the software component across the multiple projects and platform. Portability, so how the software, the adoption of the software to the different hardware platforms with the help of abstraction layer, how can that can be portable. And safety and reliability, it talks about the safety critical requirements, whether how that can be included and how that can be managed in the Autosar architecture. So these are the major key objects in the Autosar to to ensure that we should follow the standardization, scalability, and portability, and reusability, and safety, reliability. And the layer, so inside the software, it have layered architectures. So the majorly, the microcontroller is the hardware, and ECU abstraction layer and application layer. So these are the layer architectures which includes, and we have the runtime environment, that is the RTE. So it is a communication, it is the separation between the application and the hardware layer. And it to support the hardware or the application software, it should establish the communication between the different other platforms. We need a communication protocols. It includes the CAN, LIN, FlexRay, Ethernet, or the some of the protocols. It should be supported. And to identify the problem in the different areas of the components, specifically the ECU or the sensors or the actuators, any part of failures that can be identified and how that can be diagnosed with help of the software component. So that should be very, very important for the fault detection and the error handling and how system recovery. So mainly the Autosar architecture, it has categorized into three layers: the application layer, runtime environment, and basic software. So which it runs on the top of microcontroller. So these are the major three software layers, and it will runs on the hardware environment, hardware layer. So microcontroller. So we talk about the microcontroller. Microcontroller, we know it provides the interfaces to the hardware resources for the basic software. And here the basic software, it provides the services like communication, memory management, diagnostics, and hardware abstraction. Next, we have a RTE. It acts as a communication between the application layer and underlying the BSW and microcontroller layer. And application, it contains the software functions such as control algorithms and vehicle specific features. So this is the major Autosar architecture layers. And we'll go in detail, understand about the software arc layers. What are the software layers? How that can be configured? So here it is divided into services or ECU abstraction, microcontroller abstraction, and complex drivers. These are the software layers we are going to discuss in the architecture. The main focus is about the microcontroller. So the microcontroller here is the hardware resources, and top of that we have the microcontroller abstraction layer. What it provides generally, it provides the interfaces for accessing the microcontroller hardware such as GPIO and timers and the communication interfaces. Communication interfaces will be accessed. The CAN, LIN, Ethernet protocols will be accessed, and the timers are accessed on the microcontroller abstraction layer. And next we have a ECU abstraction layer. So we call as a ECU AL. So it abstracts the ECU specific hardware details and provides services to the upper layers such as memory management, flashing handling, and hardware diagnostics. Next is a part of a service layers. It includes various services like communication, CAN, LIN, Ethernet, and diagnostics, and operating system services, and security concerns. It will be a part of the services layers. Next, we have a complex drivers. We call it as a CDD here. CDD here, the complex device drivers. It specifically talks about the drivers for the hardware component that cannot be handled by the standard BSW component. It will provide low-level control and interfaces with the specific hardwares. So here, these are the part of the BSW software where it provides service layers, ECU abstraction layer, and microcontroller abstraction layer. But CDD is not a part of BSW software. But some of the hardware resource essential for communication. And on behalf of that, we have a RTE. So the RTE is specifically the middle layer that connect the application software and basic software layer, the BSW. It acts as the communication mechanism, providing services to the application software component and enabling the data exchange between the above and bottom components. Here, the RTE handles the communication between the SWC, and we need to ensure that different software components can work together even if they come from different suppliers and manufacturers. So RT plays major role on integration of all the components, and that can be work in the one software architecture. And next we have an application layer. Here the application layer is the actual vehicle functionality that are implemented. It consists of software components, SWC, which represents the specific vehicle function such as engine control, infotainment, sensors management. Generally, we called as a SWC here. This SWC are designed to modular reuse, allowing them to deploy across different vehicle platforms. SW interacts with RTE, RTE to which act as a intermediate between the application and lower layers. So the data exchange happen from the application to RTE and other lower layers. So here how this architecture is differentiated into the several layers and the components. We'll go in detail to understand. So here Autosar is a standardized automotive software architecture, and it is used to modelize and standardize the development of the ECU. It making easy for development and reuse of the software component across the various vehicle, various hardwares for various vehicles. To go in detail about the layers in the Autosar architecture, we have a application layer. It is the top of the layer. It consists of the software component SWC, which execute the application specific functions where the controlling of the motor, reading of the data, and interfaces that can be configured. And it is the independent of the hardware, and we need to ensure that software components can be reused across different ECUs. And next we have our runtime environment RTE. As we know, it is a middle of the layer between the application layer and the BSW. It handles the communication between SWC. We need to ensure that application layers can interact the BSW and hardware without knowing the detail of hardware itself. The RTE also support scheduling, event handling, and synchronizing of the task. This is the major important point in the Autosar architecture, how that can be supported. It supports the scheduling and the event handling and synchronization of the task in different platforms. Next, we have the BSW. So here the basic software. Basic software layer is the component composed of the standardized software module that provide services for such as communication, diagnostics, memory management, and hardware abstraction. It is again divided into service layers. So service layers it provides the services such as operating system supports, communication protocol, and diagnostics. And we have a ECU abstraction. So ECU abstraction is specifically talks about the hardware, detail of the external devices, how that data can be transferred when the hardware is enabled. So here we need to enable the hardware and software conditions to communicate. And next we have a MCAL. It talks about the directly interface of the microcontroller and peripherals, allowing the upper layer to remain the hardware independent. Next we have a CDD. CDD layer, it handles the non-standard and time-critical functionality that are outside the scope of standard Autosar module. Here the drivers will be there. So the drivers, it will directly interact with the hardware and bypasses the Autosar abstraction layers, which we have here. And it have the time critical and specific hardwares can be configured if it supports the driver. And we have the microcontroller. The microcontroller is the underlying hardware platform that supports the entire ECU. It contains the CPU, memory, and various internal peripherals like ADC, PWM controllers, and communication modules. In Autosar architecture, the microcontroller abstraction layer acts as interface between the microcontroller hardware and the software layers. MCall it acts about the directly interacts the microcontroller hardware, providing the drivers for various internal peripherals. So these are the in detail information about the layers that present in the BSW. And coming to the application layer, so application layer, it is on the top. So as we know, where the main functionality will be, functionalities will be configured in the application layer software. So the application layer is the actual vehicle functionalities which are implemented. To understand, it have application purpose to implement the logic and the functionality which are required for the hardware, like controlling of the motor or the reading of the sensor data and interacting with the user. And for features are, it contains well-defined software SWCs that clearly specific ports will be there. So the provider port and the required port, receiver port. So provider port is something to send the data, and receiver port which receives the data. So that can be configured via the application software, where it allows the reusability and portability of the software under different platforms. It supports both sender and receiver and client server communication thing. And mounting directly, this can be interacted with the RTE, which abstracts the hardware dependency. And high order interfaces, the ports and interfaces are the major for the communication purpose. So here, for abstraction layer, it having the two ports, the provider port and required port for the communication. So required, we call that as a receiver also. So mainly the data exchange, and we have a RTE under the application layer. Specifically, this RTE is a middle layer that connects the application layer to the basic software. The purpose is it provides the virtual ECU environment for the SWC to communicate without being aware of hardware details. It enables the inter-SWV communication and SWC BSW interaction. And features is it is the hardware independent communication between SWC and auto generated during the configuration process, and it support the task scheduling and event trigger of the SWC execution. And how this RTE is mounted, it is positioned between the application layer and basic software layer. Mainly how the interfaces will be configured, it is configured with the help of APs and SWC communication. So for application, we have a ports, provider and receiver port, but for RT, we have the APIs for communication with the different layers. Here we have a RTE APIs where it will use to connect with the SWC to sender and receiver the data. Next, we have a BSW software, the base software research. Base software. Here the base software is the service layer, ECU abstraction layer, and microcontroller layer. It will be on top of microcontroller layer. So the coming to the base software. Base software. So base software BSW is the collection of the standardized software module that provide the services and hardware abstraction. And the purpose is to enable the hardware independently, the implementation of the application by abstracting the low-level hardware details. The features is it includes the standard services like memories, communication, and diagnostics, and it divides it into three main sub-layers. That is service layer and the ECU abstraction layer and microcontroller abstraction layer. We call as a MCAP. And how it can be mounted? It is mounted on the top, on above of microcontroller and the below of RTE runtime. And how these interfaces can be configured with the RTE and the microcontroller. So we call as a APIs. It have the interfaces of the communication, CAN, DIN, and some of the diagnostics, and the memory management relevant ports will be there. So that with the help of that, we are able to configure those BSW software. And coming to the part of service layers, so service layer, it talks about the topmost layer of the BSW, where it provides the generic services such as operating system services and communication management and diagnostics. The purpose is it reuse the services required by the SWC and other BSW model. The features are operating system supported, diagnostic event manager DME, and communication stack manager PDU. So there are many other examples features that will be supported by the service layer. How it is mounted? It is mounted on top of base, it on top of microcontroller abstraction layer, and it will be in a BSW layer and below the RTE. How this will be interacted with the help of APIs, so the diagnostics, the OS stacks, and communication handling can be handled. Next will be a part of the communication services in detail that will be available. So services layers, memory services, crypt services, offboard communication services are the available in the services. We will go in detail to understand this. So it provides the uniform services for vehicle network communication and diagnostics, and hides the protocol and message properties from the application, and interfaces with the communication drivers in the MCAL via the communication hardware abstraction. And it is a hardware independent concerns, but it very depends upon the bus type, and the services may changes if the bus type changes. And we have a off-board communication services. It will facilitate the exchange of data with respect to the wired or wireless network between the different vehicles, and it includes 3 blocks, various functionalities. And next we have memory services. Mainly it have handled by the NVRAM manager. It is responsible for non-volatile data operation to read and write the data, and which stores the data in the for the next iterations or the next future purpose. And it will provide the abstraction from memory location and lower level properties. Feature includes the memory data saving, loading, and checksum management. System services is specifically talks about a group of models accessed by all the Autosar layers. Example for includes the real-time operating system and error messaging. So, and some of the services MQ dependencies, the time services, and partial issue application dependence. So these are the 4 high-level information that service layer will be provided. And next we talks about the ECU abstraction layer. ECU abstraction layer is specifically the hardware detail. It is a allow layer to remain hardware independent. It provides the unified services for the accessing the internal and external devices. The future is to handle the external purpose like the external flashing or EEPROM, and it supports the CDD when it is required. So the mounting is interface between the MCAL layer and the service layer. So here the APIs will be there, the device specific APIs, the memory and the communication IO handling will be APIs will be communicated with respect to the ECU abstraction layer. So in ECU abstraction layer, specific to this, it is a dependency provided by the APIs. So as we know, the APIs it have configured in the auto layer. It supports the IO hardware abstraction, communication hardware abstraction, wireless communication, crypto hardware abstraction, memory hardware abstraction, onboard device abstraction. We will go in detail understand about this. IO hardware abstraction, it is the abstract on the chip on onboard IO complexity, and MCU it is independent but ECU hardware dependent. Communication hardware abstraction, it hides the communication bus, control specific, and provides the APIs and data exchange purpose. And we have a crypto hardware abstraction. It secures the operation by abstracting the crypto method that will be provided to the services. Here we have the internal and external software based crypto services, and we need to ensure that the upper layers are aware about the crypto devices. And memory hardware abstraction, abstract it is the abstract of the memory location, whether it will be the on chip or on board that will be decided, and application focus only in the data, not the hardware. Onboard device abstraction, it provides the drivers for non-standard devices, the watchdog timer, and we need to ensure the consistently interfacing of the data transmission across the different modules. So these are the ECU abstraction layers components it have. And next will a part of a MCAL. So MCAL, as in the part of a BSW software, the MCAL is the overview, the lower layer of the BSW. It is directly interacting with the microcontroller hardware. It provides the access to the microcontroller internal peripherals like ADC, PWM, and GPIO. And features is highly hardware independent. It includes drivers for internal peripherals, and mounting it is a position directly on the top of the microcontroller. And how this can be interacted with the help of ADC, GPIO, and SPI and CAN. Some of the other protocols can be used for communicating with the higher above end layers. And next we have need to understand about MCAL. So microcontroller, it is a consist of the microcontroller IO devices, communication devices, and wireless communication devices, and crypto drivers, memory drivers, and microcontroller drivers. So microcontroller drivers, it talks about the peripherals or the hardware relevant timers, and how that can be accessed with the help of the core. And we have the memory drivers. It contains the drivers for accessing on the on-chip memory, such as internal flash or the internal EEPROM, and it supports the memory map devices like the external flash. Crypto drivers, it offers the drivers for on-chip cryptographic device such as SHE, secure hardware extension, and SHM, the hardware security model. And we have a wireless communication drivers. It provides the drivers for a wireless network system, and it supports both in-vehicle and off-vehicle communication. And communication driver, mainly the communication, it essentially for exchanging of the data. So to exchange of those information, we required always the drivers. It includes the drivers for within the hardware. We have some part of drivers, and externally we need to communication. We need the drivers, the CAN, LIN, or any part of the other external protocols. We need the drivers to transmit. Similarly, the internal we have the SPI and I2C. So to communicate within that, we need the drivers. And next is a part of a IO drivers. So it offers the drivers for accessing using the MIU pins, IO inputs and output pins, and include the digital analog or PWM functionalities. And next we have a complex device driver, CDD. So here the CDD main purpose is specifically layer for implementing the non-standards or time critical functionalities. So the purpose is when we use the Autosar, the complex drivers is essentially some extent it's not required, but for some activities it is required to use within the Autosar architecture. So the purpose is when the Autosar doesn't support specific features, the time constants we need to use it. The future is the hardware and application specific, and it provides direct to the MCU to the application connectivity, and it is mounted directly on the top of the microcontroller layer, and and it is interfaced with the APIs, so specific to the application and the hardware based upon the above application software, the hardware thing. The RT will help us to communicate the real-time constraints and the functionalities. This is the overview of the architecture layers. So we in detail the microcontroller. On the top of that we have the MCAL. The MCAL it have the microcontroller microcontrollers. Here we have the devices and crypto devices, wireless drivers, communication, and we have a ECU abstraction layer. We have onboard device abstraction, memory hardware abstraction, crypto hardware abstraction, wireless communication, communication hardware abstraction, and IO hardware abstraction. And we have services layer. It have the system services, memory services, crypto services, and offboard diagnostic services. and that off-board communication and some part of communication service will be included here. Above that, we have a RTE and application layer. So in detail, the of the architecture. So here we have a model in the services where we are able to have the diagnostic related. We have a diagnostic communication management, diagnostic event management, fault management will be available. Similarly, the memory, it have a the NVRAM memory, and similarly we have a code management. We have the communication management, ECU management, network management, and OS we have the different scheduling, how the scheduling or the task will be handled with respect to the services. So that will be handled here in the services layer. And the communications are like Ethernet, PDU, or the COM related, or the flex ray Ethernet, that will be handled. And we have a ECU abstraction, the firmware data. And similarly, we have a microcontroller. There are the ports or GPI ports, how this can be interfaced with the ECU abstraction layer. What are the main key components under tool? Software component. So here the Autosar software components are used for reusable and standardized, make it for easy to integrate and manage them across different projects. Configuring tools like we have a Autosar Builder and Vector DaVinci and ETAS Inca are the tools that used for the configuring and generating the Autosar software configuration. And for the development tool, like we have a IDE, integrated development environment, that will support the Autosar standards, and it include the code generation and modeling simulation can be performed. The main application scope of the Autosar, it is the strong interaction between the hardware related to the sensors or the actuators, and it connect the vehicle networks like CAN, LIN, and Flexer and Ethernet protocols. And the microcontrollers typically can support 16 and 32-bit microcontrollers, and it is a high computing controllers and requires some essential power, and it should handle some part of memories will be configured, and it is a real-time and the program execution from the internal and external flashing memories. Next, it is a part of the components and the communication through the ports in the Autosar. So it talks about the type of the ports. The required port is the R port, we usually say. It is used to the component to receive the information from the services from other components. Provider port, P port, it is used for the component to offer the information or services to the other component. And we have a Autosar interfaces, that is specifically the ports for exchanging of the data across the components with help of the APIs, where we are able to exchange the information. The main purpose is the interface, how it can be enabled and how it can be read the data and how we are able to write the data. So, and we have how that can be ports and interfaces can be created. So with the help of the tools, the model Simulink, we have an Autosar dictionary. With the help of that, we are able to configure the ports and the connectors in the Autosar. So we have the assembly connectors like linker ports between the SW components that can be established. And assembling and delegation of the connector means connecting the port and disconnecting the port. It will be easier in the Autosar architecture. And delegation connector is the link port within the same SWC high-level assemblers for internal communication. Assembly connector, it is a link port between the different SWs. This is the same SWs. Internal and external device drivers in Autosar. So internal drivers is drivers used to access the internal peripherals located within the microcontroller, like the protocols or the communication internal EEPROM, IADC, GPIOs, and the layer which are placed. The layer internal layer drivers are part of the microcontroller abstraction layer. External drivers are used to access the external peripherals located outside the microcontroller. External flash, EEPROM, watchdog diagonal, and layer placement external. Here the external drivers are part of the ECU abstraction layer. And specific case, the memory mapping devices, some external devices such as memory mapping memories can be accessed directly by the MCU. The drivers for such devices are located on the MCAL layer that being used. And the concept of interfaces and handling manager in the Autosar. So the interfaces, it is a part of the APIs where you are able to communicate with the help of APIs, where it able to enable the consistent hardware independent thing. And the handler management, it is specific to the multiple or the concurrent or asynchronous access to the devices by various kinds. The function is buffering or the queuing of the request, and control access the one or more devices with the help of handlers. And next we have a manager. So manager is found in the service layers. So the NVIDIA manager for the memory relevant and some of the components. So these are the high level information about the Autosar components and Autosar architecture. It will be having a different features and the different layers and different uh, specific components will be configured in the device.